In the crushing darkness of the Norwegian Sea, there is a boundary where the laws of war surrender to the laws of physics. At a depth of 3,000 feet, the ocean ceases to be a hiding place and becomes a vice, exerting a pressure of 1,300 pounds on every square inch of steel. This is the domain of the USS Komsomolets, a ship built to survive in a place where the weapons of its enemies simply stop working. For 40 years, the Cold War was fought in the shadows of the world's oceans, a silent game of cat and mouse played by men who never saw the sky. It was a conflict defined not by the violence of explosions, but by the mathematics of detection. By the late 1970s, the United States Navy had achieved a dominance that terrified the Kremlin. American Los Angeles-class attack submarines were masterpieces of acoustic stealth. They moved through the water like ghosts, their machinery isolated on sound-dampening rafts, their hulls coated in anechoic rubber. In a knife fight at 400 feet, the Americans always won because they always shot first. The Soviet Union knew it could not win the war of silence. Their manufacturing tolerances were looser, their turbines louder, and their pumps noisier. If they tried to match the Americans decibel for decibel, they would lose. So, the naval architects at the Rubin Design Bureau in Leningrad decided to change the battlefield entirely. They stopped looking at the ocean as a flat plane of engagement and started looking at it as a vertical column of pressure. They asked a radical question. What if we go so deep that the enemy cannot follow? This question birthed Project 685, a submarine designated Plavnik by the Soviets and Mike by NATO. To the crew who manned her, she was the Komsomolets. She was not designed to be the quietest ship in the water. She was designed to be the deepest. The strategic logic was brutal and brilliant. If you can dive to 1,000 meters, 3,300 feet, you become statistically unkillable. To understand why depth equates to immunity, one must understand the limitations of the weapon designed to kill a submarine, the torpedo. The primary weapon of the United States Navy was the Mark 48 heavyweight torpedo. It is a terrifying machine, a wire-guided robot capable of sprinting at 55 knots and tracking a target with its own active sonar. But a torpedo is not magic. It is an engine. Like any engine, a torpedo generates thrust by burning fuel. The combustion process creates exhaust gases that must be vented out of the weapon and into the water. At shallow depths, this is trivial. The pressure of the exhaust gas is much higher than the pressure of the surrounding water, so it vents easily. But as the torpedo dives, the ocean pushes back. At 1,000 meters, the water pressure is 100 atmospheres. It presses against the exhaust port with a force that rivals a hydraulic press. For a conventional torpedo engine to function at this depth, it must work twice as hard. It has to burn massive amounts of energy just to push its own exhaust out of the tailpipe. This phenomenon is known as back pressure stall. As the torpedo dives deeper to chase a target, its engine begins to suffocate. Its speed drops, its range evaporates. Its guidance sensors, stressed by the crushing weight of the water, begin to lose fidelity. The Soviet engineers realized that if they could build a submarine that operated comfortably at these crushing depths, they could simply outdive the probability of a kill. If an American submarine fired a torpedo, the Komsomolets would not need to run away. It would simply drop into the basement of the ocean. The torpedo would follow it down, choking and stalling, until it ran out of fuel and drifted harmlessly into the abyss. But surviving at 1,000 meters required a revolution in material science. The standard material for submarine construction is high-yield steel, tough, flexible, and relatively easy to weld. But steel is heavy. To build a pressure hull capable of withstanding 100 atmospheres using steel, the plating would have to be so thick that the submarine would become a massive, sinking stone. It would lose its reserve buoyancy. It would be slow, sluggish, and tactically useless. The Soviet designers needed a metal that was lighter than steel but possessed a higher strength-to-weight ratio. They needed a material that was impervious to corrosion and strong enough to hold back the weight of the world. They chose titanium. Titanium is the wonder metal of the aerospace industry, but in the world of naval shipbuilding, it is a nightmare. Specifically, the Soviets developed an alloy known as 48T, a refined mixture designed to handle the extreme compression of the deep ocean. Post-Cold War analysis suggests that this alloy had a yield strength of roughly 720 megapascals, a figure that allowed the Komsomolets to maintain a reserve buoyancy of nearly 30%, a safety margin unheard of in Western designs. However, choosing titanium was the easy part. Building with it was an industrial crusade. Titanium has a fatal flaw when it comes to construction. It is highly reactive. At room temperature, it is stable. But when heated to the melting point required for welding, titanium becomes a chemical sponge. It avidly absorbs hydrogen, nitrogen, and most dangerously, oxygen from the air. If a welder strikes an arc on a titanium plate in the presence of standard atmospheric air, the metal sucks in oxygen molecules. These molecules wedge themselves into the crystal lattice of the alloy. As the weld cools, it does not form a flexible, strong bond. It becomes a brittle ceramic. To the naked eye, the weld looks perfect, but under the stress of a deep dive, that brittle seam will shatter like glass. A hull failure at 3,000 feet is not a leak. It is an implosion that occurs faster than the human nervous system can register pain. To solve this, the Soviet Union had to turn the Submarine shipyard in Severodvinsk into a fortress of inert gas. They could not simply weld the Komsomolets in a dry dock. They had to build massive, hermetically sealed hulls, atmospheric chambers large enough to hold entire sections of a submarine hull. These chambers were flooded with pure argon. Argon is a noble gas. It does not react with other elements. By displacing the air with argon, the shipbuilders created an artificial atmosphere where titanium could be melted and fused without absorbing oxygen. The working conditions inside these argon fortresses were surreal. Human beings cannot breathe argon. The welders, the fitters, and the inspectors had to wear heavy, full-body pressurized suits supplied with oxygen through umbilical hoses. They looked less like shipwrights and more like cosmonauts walking on the surface of a hostile planet. They worked in shifts, moving slowly in their bulky suits, surrounded by the eerie green-blue glow of the welding arcs. The cost was astronomical. The logistical effort to mine the ore, refine the sponge metal, roll the plates, and transport the argon was a drain on the Soviet economy that rivaled the space program. Western analysts, observing the sheer expense of the project, nicknamed the Komsomolets the golden fish. It was said, only half-jokingly, that it would have been cheaper to construct the submarine out of solid gold. Because of this cost and complexity, the Komsomolets was never mass-produced. Project 685 was not a class of ships, it was a singularity. Only one was ever built. K-218 was a unicorn, a unique, handcrafted prototype sent out to patrol the front lines. When K-218 finally slipped into the water in 1983, she was a masterpiece of intimidation. She was sleek, fast, and heavily automated. To reduce the size of the pressure hull and minimize the life support requirements, the designers had slashed the crew size. While an American Los Angeles-class submarine carried a crew of 140, the Komsomolets was operated by just 69 men. This reduction was achieved through the Omnibus Automated Combat Control System. Computers flew the ship, sensors monitored the reactor. The human element was reduced to a managerial role. This philosophy of automation was seen as the future of the Soviet Navy, a way to remove human error from the loop and increase reaction speeds. But the most striking feature of the Komsomolets was her hull. The titanium skin gave her advantages beyond just depth. Titanium is paramagnetic. It does not retain a magnetic field. This rendered the Komsomolets invisible to the magnetic anomaly detectors, MAD, used by NATO patrol aircraft to pinpoint submerged submarines. She was a ghost to magnetic sensors and a rocket to acoustic ones. In sea trials, the Komsomolets proved the validity of the concept. She dove to 1,027 meters, a record that stands to this day for a combat submarine. Down in that abyssal darkness, the crew could hear the hull compressing, the titanium ribs groaning as they took the load. They fired dummy torpedoes, proving they could fight from the basement of the ocean. She was the perfect weapon for the final stage of the Cold War. She was designed to operate alone, far from support, hunting American carriers or lurking in the deep Atlantic, immune to the weapons that were supposed to kill her. She carried a nuclear reactor to give her unlimited range. She carried nuclear-tipped torpedoes and cruise missiles to give her unlimited power. But in their pursuit of the perfect hull, the Soviet designers had overlooked a fundamental truth of naval architecture. A submarine is a system of systems. The strength of the pressure hull means nothing if the internal components are fragile. The immunity to external pressure means nothing if the internal pressure cannot be controlled. The Komsomolets was a glass cannon. She was built to withstand the ocean, but she was packed with volatile chemistry. The reduction in crew size meant there were no spare hands to fight a fire. The reliance on automation meant that if the computer failed, the ship failed, and the use of titanium, while brilliant for depth, introduced a new risk. In the presence of high heat and pure oxygen, titanium itself can burn. As the Komsomolets prepared for her patrol in the spring of 1989, she seemed invincible. She was a marvel of the modern age, a testament to what human engineering could achieve when pushed by the existential dread of the Cold War. But she was sailing into a trap of her own making. The titanium anomaly had solved the problem of the enemy, but it had created a new set of problems that were waiting in the wiring, the pipes, and the chemical generators. The ship was ready for war. It was not ready for a spark. The deepest machine ever built was about to demonstrate that while you can engineer your way out of a torpedo attack, you cannot engineer your way out of the consequences of a system that is too complex to survive its own failure. The Ghost was leaving the harbor, heading for the deep water where it belonged, unaware that the physics it had conquered were about to turn against it. On the morning of April 7, 1989, the K-218 Komsomolets was cruising at a depth of 380 meters beneath the surface of the Norwegian Sea. She was heading north, transiting back toward the Kola Peninsula after her first operational combat patrol. The mood on board was defined by the specific quiet relief that settles over a ship at the end of a long deployment. The dangerous work of tracking American submarines and mapping the thermal layers of the Atlantic was done. The sensors were clear, the reactor was humming with the steady rhythm of a machine operating at peak efficiency. Inside the titanium hull, the 69 men of the crew were going about their routines with the relaxed efficiency of veterans. It was just after 11 a.m. The watch had recently changed. In the mess hall, the off-duty sailors were eating lunch, perhaps thinking about the fresh air and sunlight that awaited them in a few days. In the central command post, Captain Evgeny Vanin sat in the command chair, monitoring the glowing panels of the omnibus combat control system. The ship was operating in a state of perfect equilibrium. The trim was level. The speed was a leisurely 8 knots. To the outside observer, perhaps a NATO listening post hundreds of miles away, the Komsomolets was just a faint, rhythmic pulse in the background noise of the ocean. There was no indication that the most advanced submarine in the world was minutes away from destruction. The crisis did not begin with a weapon impact or a collision. It began in the loneliest part of the ship, Compartment 7. Located in the extreme stern of the vessel, Compartment 7 was a chaotic industrial space. It housed the massive hydraulic steering gears that moved the rudders and the dive planes. It contained the main drive shaft seals and the auxiliary motors. It was a space filled with high-pressure oil lines, electrical bus panels, and the hum of machinery. It was separated from the rest of the ship by a heavy, watertight bulkhead, isolating it from the turbine hall in Compartment 6. On duty in this steel cavern was a single man, Seaman Nodari Buknikashvili. He was 21 years old. The exact sequence of the initial failure remains a subject of forensic reconstruction, but the evidence points to a deadly convergence of 2 minor malfunctions. Somewhere in the tangle of machinery, a hydraulic line had likely developed a microscopic leak. Hydraulic fluid under immense pressure does not drip, it atomizes. It sprays out as a fine mist, filling the air with a flammable aerosol that looks like fog but burns like gasoline. Simultaneously, in an electrical panel nearby, a short circuit occurred. It might have been a loose wire, a degraded insulator, or a surge in the grid. A spark jumped across a gap. In a normal room, a spark might scorch a wire. In a room filled with atomized oil, a spark is a detonator. At 11:03 a.m., a flash fire erupted. It was instantaneous and violent, consuming the oxygen in the room and raising the temperature to hundreds of degrees in seconds. Buknikashvili barely had time to react. He managed to shout a brief, panicked report over the intercom. "Fire in the 7th compartment! There is smoke! I am..." The line went dead. In the central command post, the alarm panel lit up. The sensors in compartment 7 registered a catastrophic rise in temperature. Captain Vannon, staring at the red light, faced the nightmare scenario of every submariner. He knew that a fire in the stern was critical, but he also knew that the ship was designed to handle it. The Komsomolets was equipped with a chemical fire suppression system known as LOKH. Vannon ordered the activation of the system for compartment 7. This decision, though doctrinally correct, was a moral heavyweight. The system flooded the compartment with freon gas, displacing the oxygen to starve the fire. By turning the key, Vannon was effectively accepting the death of Seaman Buknikashvili to save the submarine. It was the brutal calculus of the deep: sacrifice the one to save the 68. The gas was released. The heavy steel bulkhead door connecting compartment 7 to compartment 6 was sealed. On the display screens in the control room, the officers waited for the temperature sensors to drop, indicating that the fire was out. They expected the chemistry to win. They expected the automation to work. But the fire in compartment 7 was no longer a chemical fire. It had found a new source of fuel, one that transformed it from a dangerous blaze into an uncontrollable inferno. Running through the ceiling of compartment 7 was a main line for the high-pressure air system. This system, known as the VVD, was the lifeblood of the submarine's buoyancy control. It consisted of massive banks of steel bottles filled with compressed air at 400 atmospheres, roughly 6,000 pounds per square inch. This energy was stored for one specific purpose: to violently displace water from the ballast tanks in an emergency, allowing the ship to rocket to the surface. As the initial oil fire raged, it heated the steel piping of the VVD line. Steel loses structural strength as it heats up. At 600 degrees Celsius, it becomes plastic. The internal pressure of the air inside the pipe was searching for a weakness. At 11:05 a.m., the pipe ruptured. When a high-pressure airline bursts at 400 atmospheres, it does not just leak. It acts as a gas dynamic jet. A supersonic stream of air blasted into the burning compartment. This was not inert gas. It was oxygen-rich breathing air. The rupture turned compartment 7 into a pressurized blast furnace. The influx of oxygen acted like a blacksmith's bellows on an industrial scale. The fire stopped burning just the oil and the rubber insulation. It began to burn the metal itself. Aluminum ladders melted into puddles on the deck. The steel bulkheads began to glow cherry red. The temperature spiked past 1,000 degrees Celsius. The fire suppression gas, freon, that had been dumped into the room was simply blown away by the force of the air jet. Or worse, it decomposed in the extreme heat into phosgene, a lethal nerve agent. The overpressure in the compartment was immense. The Komsomolets was designed to withstand pressure from the outside. From the crushing weight of the ocean, it was not designed to withstand high pressure from the inside. The hull was being stressed in reverse. The heat was so intense that it began to affect the titanium pressure hull itself. Titanium is prized for its strength and lightness, but it has a fatal flaw in high-temperature environments. It is reactive. In a pure oxygen environment, titanium can ignite. While the hull itself did not burn through immediately, the thermal transfer was catastrophic. On the outside of the submarine, in the freezing water of the Norwegian Sea, the ocean began to boil against the skin of the ship. The anechoic coating, the thick rubber tiles glued to the hull to absorb sonar, melted and peeled away in sheets, leaving the bare metal exposed to the sea. Inside the ship, the fire refused to stay contained. The overpressure forced the superheated gases forward. They hammered against the bulkhead separating compartment 7 from compartment 6. This steel wall was designed to be watertight and fire-resistant, but it was not designed to withstand the thermal assault of a blowtorch powered by an infinite supply of compressed air. The fire found the weak points, the cable penetrations. A modern submarine is wired like a nervous system. Thousands of electrical cables run the length of the ship, carrying power to the screws and data to the central computer. These cables must pass through the bulkheads. They are routed through stuffing tubes, metal collars packed with sealant designed to prevent water from moving between compartments. But the sealant was not designed for a pressurized oxygen fire. The heat melted the packing material. The fire burned the insulation off the cables. The flames raced along the copper wire bundles, passing through the bulkhead as if it weren't there. The fire jumped from compartment 7 to compartment 6. In compartment 6, the turbine hull, The scene was one of confusion turned to horror. The sailors stationed there found smoke pouring from the cable glands. The paint on the bulkhead blistered and blackened as the steel conducted the heat from the inferno next door. Then the arc flashes began. With the insulation burned away, high-voltage power lines shorted out against the hull. Massive sparks, blindingly bright, snapped through the smoke. These electrical faults ignited the hydraulic fluid in the local machinery. Compartment 6 joined the conflagration. In the central command post, Compartment 3, the situation deteriorated with terrifying speed. The omnibus automated control system was screaming with alarms. Sensors were failing in sequence from stern to bow. Captain Vannon could see the temperature readings spiking in compartment after compartment. The fire was moving forward, eating its way toward the reactor. Suddenly, the intercom let out a screech of static. The short circuits caused by the melting cables triggered a cascade of electrical failures. The automatic safety systems on the nuclear reactor, detecting the chaos in the grid, triggered a scram. The control rods dropped, the reactor shut down, the Komsomolets lost propulsion. The submarine was now drifting at 380 meters without power, with a fire raging in the stern that was hotter than the melting point of steel. The silence of the electric motors was replaced by the distant, muffled roar of the inferno and the groaning of the titanium hull. Captain Vannon realized that the automation had failed. The fire was not contained, it was spreading. And with the propulsion gone, the dynamic lift that helped keep the heavy submarine at depth was lost. They were in danger of sinking below their crush depth. He ordered the ship to surface. Emergency ballast blow! This was the maneuver the Komsomolets was designed for. The high-pressure air banks in the forward section, those not compromised by the fire, opened. A torrent of gas rushed into the ballast tanks to displace the water. The submarine surged upward. It rose through the water column, accelerating like a rocket. It breached the surface of the Norwegian Sea at 11:16 a.m., rolling violently in the heavy swell. For a moment, the crew might have felt a surge of hope. They were on the surface. They were in the open air. The immediate threat of being crushed by the depth was gone. They believed they had escaped the trap, but they were wrong. By surfacing, they had not solved the problem, they had exacerbated it. The fire in the stern was still being fed by the ruptured airline. The heat had nowhere to go now that the hull wasn't surrounded by the crushing cold of the deep. And more dangerously, the electrical shorts caused by the fire were wreaking havoc on the ship's internal systems. The arcing continued. High-voltage lines touched the titanium hull or each other. Arcs of electricity, powerful enough to blind a man, snapped through the machinery spaces. The crew was now fighting a battle they were not equipped for. The reduced manning levels meant there were simply not enough people to handle the hoses, communicate with command, and monitor the spreading toxicity all at once. Men were running from station to station, exhausted and confused. The smoke began to fill the ventilation system. It was a thick, acrid smoke, laced with carbon monoxide and the toxic byproducts of burning plastic and rubber. It seeped into the living quarters. It crept into the control room. In Compartment 6, the sailors who had been stationed there were trapped. The fire had breached the bulkhead from Compartment 7. They were caught between the inferno behind them and the sealed door forward. The automated fire suppression system in their compartment likely triggered, dumping freon into the air, displacing the oxygen they needed to breathe. They died not from the flames, but from the system designed to save them. The Komsomolets was the most advanced submarine in the world, but as it bobbed on the gray waves of the Arctic, it was helpless. The titanium hull, built to withstand the pressure of 1,000 meters, was being eaten from the inside by a fire that the automation had failed to stop. The spark in the stern had grown into a monster. The decision to reduce the crew size, to rely on the Almaz system and the chemical extinguishers, was now exacting its price. There were no spare hands to save the ship. There was only the fire, the smoke, and the terrifying realization that the technology they trusted had become an accomplice to the disaster. The boat was on the surface, but it was not safe. The fire was feeding on the very air supplies meant to keep the submarine buoyant. The Komsomolets was burning, and she was beginning to settle back into the water. The struggle for the depths was over. The struggle for the surface had just begun. When the K-218 Komsomolets broke the surface of the Norwegian Sea at 11:16 a.m., the crew experienced a cruel biological deception. The hatch in the sail was thrown open, and the freezing, clean air of the Arctic rushed into the stale atmosphere of the command center. To the men gasping in the smoke, this felt like salvation. They believed that by reaching the surface, they had escaped the trap. They believed that the infinite supply of oxygen outside would allow them to breathe. They did not realize that the submarine itself was also taking a breath. And for the fire raging in the stern, that breath was the catalyst for a thermal runaway that would doom the ship. In the closed environment of a submerged submarine, a fire is self-limiting. It consumes the available oxygen and eventually chokes itself out. But by surfacing and opening the hatch, the crew had inadvertently turned the Komsomolets into a chimney. The fire in compartments 6 and 7 was the heat source. The open hatch in the sail was the exhaust vent. The fresh air being sucked down through the main induction valves and the open hatch acted as the intake. The draft created by this airflow did not cool the fire, it stoked it. The flames, which had been struggling against the combustion products in the stern, suddenly roared with renewed vigor. The temperature in the turbine hull began to climb again, passing the melting point of aluminum and approaching the structural limits of the titanium bulkheads. But the fire was about to find a fuel source far more volatile than diesel oil or rubber insulation. It was about to find the oxygen generators. Every submarine is a closed ecological system. To keep the crew alive while submerged for months, the ship must manufacture its own breathable atmosphere. The Komsomolets used a chemical system known as the V64 Air Regeneration Unit. These devices rely on canisters filled with potassium superoxide, a chemical powder that absorbs carbon dioxide and releases pure oxygen in a chemical reaction. It is a brilliant piece of life support engineering, but potassium superoxide is also a potent oxidizer. It is chemically unstable at high temperatures. In a normal environment, the canisters are safe. In a compartment where the ambient temperature has exceeded 800 degrees Celsius, the steel casings of the V64 units lose their structural integrity. They warp. They crack. At approximately 11:21 a.m., just 5 minutes after surfacing, the V64 units in compartment 6 began to detonate. These were not simple mechanical failures, they were chemical explosions. As the casings burst, they released their inventory of pure oxygen directly into the heart of an oil-fed fire. The effect was similar to throwing a bucket of gasoline onto a bonfire, but infinitely more intense. Oxygen does not burn, but it allows other things to burn at temperatures that defy standard physics. The fire flashed over instantly. The flashover created a shockwave of pressure and heat that rocked the entire submarine, felt by the survivors standing on the deck casing hundreds of feet away. The environment in the stern compartments transitioned from an industrial fire to a thermal catastrophe. The fire was now burning hot enough to vaporize the internal structures. The aluminum ventilation trunks, the copper wiring, and the steel deck plates were being consumed. This thermal violence created a new problem: the loss of containment. The Komsomolets was built with a titanium pressure hull, a material chosen for its immense strength. But titanium has a specific vulnerability. It conducts heat. As the fire turned the internal compartments into a furnace, the heat transferred through the hull to the rubber anechoic tiles on the exterior. The ocean around the stern of the submarine began to boil. The tiles peeled off, leaving the naked metal exposed to the thermal shock of the freezing sea. Inside, the fire began to eat through the seals that kept the ship watertight. A submarine hull is pierced by thousands of penetrations, holes for cables, pipes, and drive shafts. These holes are sealed with cable glands, usually made of specialized rubber or polymer packing. At 1,000 degrees, the packing material vaporized. The watertight bulkheads, designed to isolate the flooding, became sieves. The fire burned through the cable runs, creating open tunnels between the compartments. The smoke, driven by the overpressure of the oxygen explosion, surged forward. This smoke was not the gray wood smoke of a campfire, it was a thick, black chemical soup. It contained hydrogen chloride from burning plastic, phosgene from decomposed freon, and massive quantities of carbon monoxide. Carbon monoxide is the silent assassin of the submarine service. It is odorless, colorless, and binds to the blood's hemoglobin with a ferocity that prevents oxygen transport. A concentration of just 1.28% in the air causes unconsciousness after 2 or 3 breaths and death in 3 minutes. The smoke traveled through the ventilation system, bypassing the sealed doors. It entered the living quarters in compartment 4 and the central command post in compartment 3. The crew in the forward sections, who had believed they were safe from the fire in the stern, suddenly found themselves in a gas chamber. Men began to cough. Their vision blurred. They felt a sudden, overwhelming lethargy. The discipline of the damage control parties began to fracture not because of panic, but because the men were physically incapable of thinking. They donned their emergency breathing masks, the IP-46 rebreathers. These masks are chemical units similar to the oxygen generators. You pull a starter tab, a chemical reaction starts, and you breathe into a closed bag. But using them requires training and calm. In the chaos of the smoke, with hands shaking and eyes blinded by tears, men struggled to activate them. Some masks were old, the chemicals had degraded. Some men didn't get them on in time. In the control room, Captain Vanin was fighting a battle against a ship that was disintegrating around him. The omnibus automation system was dead, its sensors melted or shorted out. He was receiving reports via voice pipe and runner, but the reports were fragmented and terrifying. Compartment 5 is filling with smoke. Pressure rising in compartment 6. We are losing buoyancy. This was the critical turning point. The fire had destroyed the integrity of the high-pressure air (VVD) system in the stern. The air that was supposed to keep the ship afloat had vented into the fire. Now, the vacuum left by the cooling gas and the breach of the hull seals allowed the ocean to enter. Water was flooding into compartment 7. It hissed as it hit the superheated metal, flashing into steam, but the volume of water was too great. The stern of the submarine began to get heavy. On the surface, the trim of the ship changed. The bow rose slightly, the stern settled deeper. It was a subtle shift at first, barely noticeable in the heavy swell, but to a trained eye, it was the signature of a dying ship. The failed suppression was total. The chemical lock system had failed because of pressure. The isolation protocol had failed because of the cable runs. The surfacing maneuver had failed because of the draft. And the oxygen generators, the life support system, had turned into bombs. Every system designed to save the ship had conspired to destroy it. By 2 p.m., the situation in the forward compartments was becoming untenable. The concentration of carbon monoxide was rising. The men who were not wearing masks were passing out. The ship's doctor moved among them, administering aid, but he was fighting a losing battle against chemistry. There is no antidote for carbon monoxide poisoning in a submarine filled with smoke. The only cure is fresh air, and the air inside was poison. Captain Vanin realized that the internal battle was lost. They could not put out the fire, they could not stop the smoke, and now they could not stop the water. The Komsomolets was transitioning from a burning vessel to a sinking one. Vanin ordered the classified documents to be secured. He ordered the crew to prepare for evacuation. But evacuation on a submarine is not like on a cruise ship. There are no lifeboats on davits. There are inflatable rafts stored in canisters in the superstructure, but deploying them requires men to go out onto the wet, slippery deck in freezing wind and waves. The crew began to move up the ladders. They emerged from the hatch into the biting cold of the Norwegian Sea. They were covered in soot, vomiting from smoke inhalation, and shivering in their thin cotton uniforms. They looked back at the sail of their ship. The titanium skin was discolored by heat. Smoke was still puffing from the vents. The ship looked like a wounded beast, thrashing in the water. But inside the hull, the reactor was the final variable. The automatic scram had dropped the rods hours ago. The core was shut down. But without the cooling pumps running, the residual decay heat was building up. The reactor vessel was getting hot. The danger now was not a nuclear explosion, but a breach of the primary coolant loop. If the heat warped the pipes or the seals failed, the radioactive water from the core would mix with the floodwater entering the ship. The Komsomolets would become an open radiological source. Vanin stayed below. He felt the deck angle steepen. He watched the depth gauge in the control room, even though the ship was on the surface. He was monitoring the trim. He knew that once the water breached the main hatches in the stern, the reserve buoyancy would vanish. The failure of the suppression efforts on the Komsomolets is a lesson in the complexity of disaster. It wasn't one thing that went wrong, it was the interaction of systems. The air system fed the fire. The fire burst the oxygen generators. The generators melted the seals. The seals let in the smoke. The smoke killed the crew's ability to fight. It was a cascade of unintended consequences. The designers had optimized the ship for a war against the Americans, but they had not optimized it for a war against entropy. They had built a ship that could survive a torpedo, but not a short circuit. As the afternoon light began to fade over the Arctic, the Komsomolets settled lower. The waves began to wash over the aft casing. The steam hissing from the hot hull mixed with the sea spray. The submarine was preparing for her final dive, and the men on the deck, coughing the poison out of their lungs, realized that the fire was no longer their biggest problem. The water was coming, and it was freezing. At 4:30 p.m. on April 7, 1989, the K-218 Komsomolets lay wallowing on the surface of the Norwegian Sea, a black scar against the gray water. Smoke continued to pour from the stern, trailing downwind like a dark banner, but for the crew huddled on the outer casing, the immediate terror of the fire had been replaced by a strange, deceptive calm. They were alive, they had fought the inferno, shut down the reactor, and brought the ship to the surface. To a sailor, the surface is the finish line. It is the place where the laws of the ocean yield to the laws of man. They believed they had survived the worst. They were wrong. They had merely traded a quick death by fire for a slow death by ice. The tragedy of the next few hours was not a failure of engineering, but a failure of logistics and doctrine. The Soviet Navy was built to fight a global war. It possessed thousands of ships, aircraft, and submarines. Yet, in the middle of a peacetime disaster, the fleet found itself paralyzed by the tyranny of distance and the unforgiving physics of the Arctic environment. The first asset to arrive on the scene was not a rescue ship, but an aircraft. An Ilyushin Il-38 maritime patrol plane, scrambled from the airbase at Severomorsk, circled overhead. The pilot, Major Petrogradsky, looked down and saw the stricken submarine. He saw the smoke. He saw the men gathering on the deck. He established radio contact with Captain Vanin. "I see you," he reported. "Help is on the way." For the men on the casing, the sight of the aircraft was a lifeline. It was a tangible connection to the motherland. It meant they were not alone. But an airplane cannot lift 60 men off a burning deck. It cannot stop a submarine from sinking. It can only watch. The nearest surface vessels were the Alexei Klobistov, a massive fish processing factory ship, and the Oma, a fishing trawler. They were ordered to divert to the scene at maximum speed. But maximum speed for a commercial fishing vessel in heavy seas is barely 12 knots. They were dozens of miles away. The math was brutal. The ships would need hours to arrive. The Komsomolets did not have hours. The fire in the stern had destroyed the watertight integrity of the pressure hull. The titanium, weakened by the heat, had warped. The seals on the propeller shafts had melted. Water was flooding into Compartment 7 and Compartment 6 faster than the pumps could remove it, even if the pumps had been working, which they weren't. The submarine began to settle by the stern. The trim angle increased. The bow rose higher into the air while the tail slipped beneath the waves. The massive titanium rudder, usually hidden underwater, broke the surface, looking like the fin of a dying leviathan. Captain Vanin, realizing the ship was lost, gave the final order: abandon ship. This is the moment where the disaster shifted from a mechanical crisis to a biological one. The crew began to deploy the life rafts. The Komsomolets was equipped with inflatable rafts stored in canisters in the superstructure, designed to deploy automatically or manually. But the systems failed. One raft capsule failed to open, its release mechanism jammed by ice or corrosion. Another deployed but was blown away by the wind before it could be secured. The line snapped. A third raft inflated upside down. The crew, exhausted and poisoned by carbon monoxide, struggled with the heavy gear. Their hands were numb. Their coordination was gone. And then the submarine gave up. At 5:08 p.m., the stern dropped sharply. The Komsomolets slid backward, accelerating into the depths. The water rushed over the casing, washing the men into the sea. There was no explosion, no dramatic breakup. One moment, the ship was there, a solid island of titanium. The next, it was gone, leaving 60 men floating in the freezing water of the Norwegian Sea. The water temperature was 2 degrees Celsius, roughly 35 degrees Fahrenheit. In these conditions, the human body enters a state of physiological shock. When a person is plunged into near-freezing water, the cold shock response triggers an uncontrollable gasp reflex. If a sailor's head is underwater when he gasps, he drowns instantly. Those who managed to keep their heads above water faced the next enemy: thermal conductivity. Water conducts heat away from the body 25 times faster than air. The cold does not just chill the skin, it penetrates to the core. It steals the metabolic heat generated by the heart and liver. The biological timeline of survival in the Norwegian Sea is terrifyingly short. Minutes 0 to 5. The extremities begin to cool. The blood vessels in the arms and legs constrict violently to preserve core heat. This causes a loss of dexterity. Fingers become useless claws. Men cannot undo buttons, zip jackets, or grip the ropes of the life rafts. Minutes to 15. The muscles begin to fail. Swimming becomes impossible. The cold penetrates the nerve fibers, slowing the transmission of signals. The men in the water begin to lose the ability to tread water. Even with life vests, the struggle to keep the face out of the waves becomes exhausting. Minutes 15 to 30. Hypothermia sets in. The core body temperature drops below 95 degrees Fahrenheit. Shivering becomes violent and uncontrollable, then stops as the body runs out of energy. Cognitive function degrades, the mind becomes foggy, hallucinations begin. Men stop feeling the cold, they start to feel a deceptive warmth, a sign that the brain is dying. The crew of the Komsomolets was fighting this timeline without immersion suits. Most were wearing standard naval uniforms, cotton and wool that soaked up water and dragged them down. Only a few had managed to don bulky thermal protection suits, and even those were imperfect. They clustered in the water, trying to share body heat. They sang songs to keep morale up. They called out names. But the ocean was indifferent to their courage. One by one, the voices fell silent. The pilot of the Il-38 watched from above, helpless. He dropped rescue canisters, but the wind scattered them. He saw the men drifting apart, small black dots in a vast gray killing field. The tragedy was compounded by the failure of the rafts. The single large raft that had deployed successfully was overcrowded. Men clung to the sides, their bodies submerged in the freezing water. The raft was too small for the entire crew. Those on the raft tried to pull their shipmates aboard, but their strength was gone. A man in the final stages of hypothermia is dead weight. He cannot help himself. To lift a 200-pound, waterlogged body over the high gunwale of a rubber raft requires immense strength that the survivors did not have. The cold weight became a slow-motion massacre. It took nearly an hour and a half for the Alexei Klobistov to arrive. The fishing factory ship steamed into the debris field at 6:20 p.m. Her crew lined the rails, throwing nets and ropes. They launched their own small boats. But for many of the Komsomolets sailors, it was too late. They were floating, but they were gone. Their hearts had stopped from the cold. The fishermen pulled bodies from the water. They pulled survivors who were so cold they looked like corpses. They carried them to the ship's infirmary, stripped off their wet clothes, and tried to warm them with blankets and body heat. Of the 69 men who had sailed on the Komsomolets, 42 died. Only a handful died from the fire or the explosion. The vast majority died in the water, waiting for a rescue that was too slow. They died because the Soviet Navy had assumed that a submarine on the surface was safe. They died because the logistical chain of rescue was broken. The disaster revealed a glaring gap in Soviet naval capabilities. The Western navies, the US and the UK, maintained dedicated submarine rescue forces on high alert. They had helicopters capable of winching men from the water in minutes. They had long-range rescue aircraft that could drop large, self-inflating rafts. The Soviet Northern Fleet had relied on the assumption that their own surface ships would be close enough to help. But the Komsomolets had been operating alone, far from the support of the fleet. The Bastion strategy assumed protection. But the ocean is too big for assumptions. Among the dead was the ship's doctor. He had spent his final moments in the water moving from man to man, checking pulses, offering words of encouragement, until the cold took him too. There was also a grim irony in the fate of the classified documents. As the ship sank, some officers had prioritized saving the code books and the logs. They stuffed them into their jackets, believing they were protecting state secrets. But the weight of the paper and the bindings helped drag them down. In the end, the secrets were lost anyway, dissolving in the salt water along with the men who carried them. The survivors on the Klobistov were in shock. They were trembling, weeping, and silent. They had survived the fire. They had survived the reactor. They had survived the sinking, but they had watched their friends freeze to death inches away from safety. The loss of the Komsomolets was not just a naval disaster, it was a human catastrophe caused by a doctrinal blind spot. The obsession with the submarine's performance, its depth, its speed, its automation, had overshadowed the basic requirements of crew survival. The designers had spent millions of rubles on titanium welding and automated sensors, but they had not ensured that the life rafts would open. They had built a spaceship for the ocean, but forgot to give the astronauts a parachute that worked. As the Alexei Klobostov turned toward the coast, carrying the living and the dead, the sun began to set over the Norwegian Sea. The water was empty again. The Komsomolets was gone, falling through the darkness toward the seabed, taking the reactor and the torpedoes with her. But the story was not quite over. As the main hull vanished, one final drama was playing out deep beneath the surface. Captain Vannon and 4 other men had not gone into the water. They were still inside the submarine when it sank. They were trapped in the escape capsule, the ultimate insurance policy that the designers had promised would save them. As the submarine passed crushed depth, they were about to discover the final, fatal flaw in the design of Project 685. The ship was dead, but the capsule was about to make one last desperate attempt to reach the surface. While the survivors on the surface of the Norwegian Sea were fighting their losing battle against the cold, a different, more claustrophobic tragedy was unfolding deep beneath them. The sinking of the K-218 Komsomolets was not an instantaneous event for everyone. For 5 men, the death of the ship was not the end of the struggle. It was the beginning of a descent into the crushing darkness of the abyss, trapped inside a machine that had promised them safety but delivered them into a nightmare of physics. Captain Evgeny Vannon had not abandoned his ship. Adhering to the ancient, grim tradition of the sea, he had remained in the central command post until the water was washing over the bridge. He had sent the crew up the ladders, watching them disappear into the smoke and the spray. But as the angle of the deck steepened and the stern slipped under, Vannon heard voices on the intercom. There were men still alive inside the hull. One of them was Captain Lieutenant Ispenkov, the engineering officer responsible for the electrical plant. While the rest of the crew scrambled for the life rafts, Ispenkov had remained at his post in the machinery space. He was keeping the diesel generator running. He knew that if the power died, the lights would go out, the radios would fail, and the pumps would stop. He was the man keeping the heart of the ship beating while it died. When the order finally came to evacuate, the path to the bridge was cut off by water and fire. Ispenkov was trapped deep in the hull, listening to the generator hum, waiting for the ocean to take him. He would go down with his engine, a sacrifice of absolute devotion. But for Captain Vannon and a small group of others, Captain Lieutenant Yudin, Midshipman Slyusarenko, and Midshipman Chernikov, there was one remaining option. It was a feature that no American submarine possessed, a piece of engineering bravado that symbolized the Soviet approach to survival. Built into the massive sail of the Komsomolets was a detachable escape capsule known as the VSK, Vspomogatelnaya Spasatelnaya Kamera. The VSK was essentially a submarine within a submarine. It was a reinforced titanium lifeboat, roughly the size of a small elevator, capable of holding the entire crew in an emergency. It had its own independent air supply, its own battery, and its own release mechanism. In theory, if the submarine was lost at extreme depth, the crew could climb into the VSK, seal the hatch, and jettison the pod. It would rocket to the surface, preserving the lives of the sailors even as the main hull was crushed. It was the ultimate insurance policy, a technological marvel. But like the automated fire systems and the oxygen generators, it had never been tested in the chaos of a real disaster. As the Komsomolets began her terminal plunge, sliding backward into the deep, Vanin, Yudin, Slyusarenko, and Chernikov scrambled into the bottom hatch of the escape capsule. The environment they entered was horrific. The interior of the submarine was dark, illuminated only by the dying flickers of emergency lights. The air was thick with carbon monoxide and hydrogen chloride. The men were coughing, their eyes burning, their minds clouded by the toxic gas. They climbed into the capsule and sealed the lower hatch. They were now inside a titanium egg trapped inside a sinking ship. The sensation of the descent was sickening. They were falling backward. The depth gauge in the capsule spun 100 meters, 200 meters, 400 meters. The pressure on the outside of the hull was increasing by 1 atmosphere every 10 meters. The men worked frantically to activate the separation sequence. They threw the levers that should have fired the explosive bolts, severing the connections between the capsule and the sail. Nothing happened. The release mechanism had jammed, whether it was due to the heat warping the metal, the angle of the descent, or a failure in the electrical firing circuits. The ultimate insurance policy was refusing to pay out. The VSK remained locked to the Komsomolets, dragging the men down toward the crush depth. Panic, cold, and absolute must have set in. They were passing 600 meters. The hull of the main submarine began to groan under the pressure. Even the mighty titanium ribs could not withstand the ocean forever. If the capsule did not separate soon, the main hull would implode and the shockwave would shatter the VSK instantly. Captain Vannon, fighting through the fog of carbon monoxide poisoning, realized that the automatic systems had failed. He ordered the manual release. This involved a physical override, a desperate application of muscle against machinery in a confined, gas-filled space. At a depth of approximately 1,600 meters, a mile down, in the absolute darkness of the abyss, physics intervened. It wasn't the manual release that saved them, it was the chemistry in the bow. The forward torpedo room of the Komsomolets housed massive banks of silver-zinc batteries. As the ship sank and flooded, the seawater mixed with the battery electrolytes. This reaction generated vast quantities of hydrogen gas. At 1,600 meters, the pressure compressed this gas, creating a volatile, high-density pocket of explosive potential. The hydrogen detonated. A massive internal explosion ripped through the forward compartments of the submarine. The shockwave traveled down the titanium spine of the ship, hitting the sail like a hammer. The vibration shattered the friction locks and the jam bolts holding the capsule. The ship died, but in its death throes, it hammered the capsule free. The buoyancy of the capsule took over. Freed from the dead weight of the submarine, the VSK shot upward. It accelerated like a missile, rushing toward the surface. But the physics of this ascent created a new, deadly problem. The capsule was not empty of air. It was filled with the atmosphere it had inhaled from the burning submarine before the hatch was sealed. That atmosphere was a toxic soup of smoke and carbon monoxide. Worse, it was pressurized. As the submarine had sunk, the internal pressure had increased due to the leaks and the fire. Now, as the capsule rocketed upward, the pressure outside was decreasing rapidly. This is the physics of the bends, but on a macroscopic scale. The gas inside the capsule began to expand. The partial pressure of the carbon monoxide increased. The toxic effect on the men intensified. They were trapped in a rising gas chamber. Midshipman Chernikov and Captain Lieutenant Uden began to lose consciousness. The carbon monoxide was binding to their blood cells, starving their brains of oxygen. Captain Vannon was fading. Only Midshipman Slusarenko, perhaps due to his position in the capsule or a quirk of physiology, managed to remain somewhat alert. He struggled to put on his breathing mask, but the connections were difficult to manage in the cramped, dark space. The ascent took only a few minutes. The capsule breached the surface of the Norwegian Sea with explosive violence. It did not bob gently. It erupted from the water like a cork shot from a cannon, leaping into the air before crashing back down. The sudden change in pressure was the final blow. The internal pressure of the capsule was vastly higher than the atmospheric pressure outside. The top hatch, which was supposed to be opened manually by the crew, was blown off by the force of the expanding gas. The explosion of the hatch was catastrophic. Midshipman Chernikov, who had been standing near the top of the capsule, was ejected. The force of the decompression threw him out of the hatch and into the turbulent sea. He was killed instantly, either by the trauma of the ejection or by drowning in his unconscious state. Midshipman Slusarenko was also blown out. He flew through the open hatch and landed in the water yards away. He was dazed, suffering from decompression sickness and gas poisoning, but he was alive. The cold shock of the water revived him. Inside the capsule, Captain Vannon and Captain Lieutenant Uden remained. They were unconscious, overcome by the gas and the sudden pressure drop. They could not move. The capsule, now open to the sea, began to take on water. The waves, driven by the winds that had doomed the life rafts, washed over the low freeboard of the VSK. The heavy titanium shell, which had just performed the miracle of lifting them from the abyss, lost its buoyancy. Sluyusarenko, treading water in the freezing swell, watched in horror. He saw the capsule bobbing for a few moments. He shouted for his captain, but there was no response. The gas had done its work. The VSK flooded, it tilted, and then, for the second time that day, it sank. It slid beneath the waves, carrying Captain Vannon and Captain Lieutenant Uden back down to the wreck of the submarine they had tried so hard to save. They had traveled from the surface to the bottom, back to the surface, and then back to the bottom again. It was a cruel Sisyphean tragedy. Sluyusarenko was left alone in the water. He was the sole survivor of the capsule group. He was eventually picked up by the rescue boats from the Alexei Klobistov, a miraculous survivor in a sea of ghosts. The failure of the VSK was not a mechanical failure of the lifting body. The capsule had physically worked. It had separated and surfaced. The failure was systemic. The designers had built a machine to escape a sinking submarine, but they had not accounted for the atmosphere inside that submarine. The capsule's ventilation system had drawn in the smoke before launch. The mask connection points designed to feed the crew clean air from a built-in supply were difficult to use in the chaos. The overpressure relief valves, which should have equalized the pressure during the ascent to prevent the hatch from blowing, were either not activated or insufficient for the speed of the rise. It was the empty boat philosophy carried to its tragic conclusion. The system relied on perfect conditions to save lives. It assumed that the crew would be calm, that the air would be breathable, and that the physics would be predictable. But in a fire, nothing is clean and nothing is predictable. The death of Captain Vannon is a polarizing subject in naval history. Some view him as a hero who stayed to the end, a captain who refused to leave his ship until there was no ship left. Others view him as a victim of his own rigidity, a man who trusted the automation too much and waited too long to order the evacuation. But his final moments in the capsule reveal the ultimate betrayal of the Soviet design philosophy. He was a man trapped in a machine that was supposed to save him. He had done everything the manual required. He had triggered the system, and the system had killed him. The sinking of the escape capsule marked the end of the active phase of the disaster. The Komsomolets was gone. 42 men were dead. The survivors were huddled in the sick bay of a fishing boat sailing toward Murmansk. But as the ocean closed over the site, a new, slower disaster was beginning. The Komsomolets had not gone down empty. She was a nuclear-powered warship. She carried a reactor core loaded with uranium. She carried 2 torpedoes tipped with plutonium warheads. She was now resting at a depth of 1,680 meters. The pressure at that depth is immense. The salt water is corrosive, and the titanium hull, which had been the pride of the Soviet fleet, was now a sealed container for a radiological poison that would not decay for thousands of years. The world had watched the fire. Now the world would have to watch the water. The submarine was silent, but the isotopes inside her were restless. The environmental clock had started ticking, and the Komsomolets was about to become the most dangerous shipwreck on Earth. 1 mile beneath the surface of the Norwegian Sea, the darkness is absolute and the pressure is 160 atmospheres. In this crushing, freezing void, the wreck of the K-218 Komsomolets rests on the sediment of the Bear Island Trough. She landed upright, her titanium hull buried deep in the mud, her sail standing proud like a tombstone. The violence of the fire and the sinking is over. The screaming of the air vents and the shouting of the men have been replaced by the eternal silence of the abyss. But inside the wreck, a different kind of activity continues. It is silent, invisible, and terrifyingly slow. It is the activity of the atom and the electron. The Komsomolets did not go down alone. She took with her a nuclear reactor fueled by highly enriched uranium and 2 torpedoes tipped with plutonium warheads. For the first few years after the disaster, the Soviet government, and later the Russian Federation, insisted that the wreck was safe. They argued that the titanium hull was impervious to corrosion, that the reactor was sealed, and that the depth would act as a permanent quarantine. They were wrong. The ocean is a patient adversary. While titanium is indeed resistant to corrosion, the internal components of the submarine were made of steel, copper, and aluminum. The galvanic reaction between these dissimilar metals, immersed in an electrolyte of salt water, turned the wreck into a massive battery. The metal began to dissolve. In the early 1990s, independent expeditions led by Russian scientists and monitored by Norwegian environmentalists began to visit the site using deep-diving Mir submersibles. What they found was a disturbing reality that contradicted the official assurances. The submarine was not inert, it was breathing. The fire that had destroyed the ship had also damaged the ventilation pipes, causing the reactor compartment to be open to the sea. The currents flowing through the wreck were washing over the reactor vessel. The sensors on the submersibles began to pick up spikes of cesium-137, a radioactive isotope produced by nuclear fission. The reactor was leaking. It was not a catastrophic gusher, but a pulsing release. As the tide changed and the deep-sea currents shifted, clouds of radioactive water were being pumped out of the hull and into the surrounding ocean. In 2019, a joint Norwegian-Russian expedition captured high-definition video of this phenomenon. The footage showed a ghostly, whitish cloud drifting out of a ventilation pipe near the reactor casing. When the ROV's robotic arm took a water sample directly from the cloud, the analysis showed cesium-137 levels that were 800,000 times higher than normal seawater. So far, the dilution factor of the ocean has prevented a wider catastrophe. The Norwegian Sea is vast, and the isotopes are dispersed quickly. But the reactor is not the only threat. In the bow of the submarine, in the torpedo tubes, lie two nuclear-tipped torpedoes. The warheads contain plutonium-239. Plutonium behaves very differently from cesium. Cesium is soluble, it dissolves in water and drifts away. Plutonium is heavy and chemically reactive. It tends to bind to particles of sediment. If the torpedo casings corrode and the warheads are exposed, the plutonium will not drift away. It will settle on the seafloor, creating a localized dead zone of intense toxicity. Here, the titanium hull creates a unique problem: galvanic corrosion. When two different metals are immersed in salt water and connected electrically, they form a battery. One metal becomes the anode and corrodes, while the other becomes the cathode and is protected. Titanium is a very noble metal. Steel is less noble. The hull of the Komsomolets is a massive cathode. The internal machinery, the reactor vessel, and the torpedo casings are made of steel alloys. They are the anodes. The titanium hull is effectively accelerating the corrosion of the steel components inside it. The miracle metal that protects the ship from the outside is eating it alive from the inside. This electrochemical suicide pact means that the containment barriers of the reactor and the torpedoes are degrading faster than they would in a conventional steel wreck. The clock is ticking faster on the Komsomolets. In the 1990s, the Russian government debated raising the submarine. The fear was that the corrosion would eventually cause a catastrophic release of plutonium. But the engineering reality was grim. The titanium hull, though strong, is brittle. The fire damage had weakened the structure in unpredictable ways. Trying to lift the ship from a mile down could cause it to break apart, spilling its nuclear guts into the water column. Instead, they chose a strategy of containment. In a series of daring expeditions, Russian engineers used ROVs to seal the torpedo tubes with massive titanium caps. They pumped a specialized jelly-like sealant into the bow section, designed to inhibit corrosion and trap any loose plutonium. They covered the ventilation openings with rubberized blankets. It was a desperate, high-tech attempt to bandage a mortal wound. It bought time, but it did not solve the problem. The sealant will eventually degrade, the blankets will rot. The galvanic corrosion continues, electron by electron. The Komsomolets remains a paradox. It was built to be the ultimate survivor, a ship that could hide where no one could follow. Now, it is hiding a nuclear secret in the one place where we cannot easily fix it. It serves as a dark monument to the philosophy of performance over safety. The designers achieved their goal of building a ship that could withstand the deep ocean, but they failed to build a ship that could survive itself. For the families of the 42 men who died, the site is a grave. Every year, on April 7th, sirens sound at the naval base in Vidyayevo. Wreaths are cast onto the water. The names are read: Captain Evgeny Vanin, Seaman Nodari Buknikashvili, Captain Lieutenant Ispenkov. They are remembered not as victims of a faulty machine, but as men who stood at their posts while the air turned to fire and the water turned to ice. They did what they were trained to do. They fought for the ship until the ship could no longer be fought for. The story of the Komsomolets is a warning about the seduction of technology. We build machines to conquer nature, to dive deeper, fly faster, and hit harder. But nature always holds the veto. The titanium hull could withstand the pressure of the deep, but it could not withstand the pressure of a broken pipe. The automation could fly the ship, but it could not save the crew. In the end, the depth forgave nothing. The Komsomolets was built to be the ultimate survivor, but she rests now in the dark, a lesson written in titanium and blood. She reminds us that no matter how advanced our engineering becomes, the sea remains a wilderness, and the price of entry is always, eventually, paid in full. The ghost is still down there, waiting, and as long as the isotopes glow in the dark, the story of the Komsomolets is not over. It is just drifting in the current, a silent signal from the past to the future, warning us to respect the things we build and to fear the things we cannot control. The tragedy of the Komsomolets is distinct from other submarine disasters because it was not caused by an enemy, a collision, or a navigational error. It was caused by a philosophy. It was the result of a deliberate choice to prioritize performance over resilience and automation over humanity. There is a profound sadness in the image of the escape capsule, the technological miracle designed to save the crew, becoming the final coffin for the captain. It represents the ultimate betrayal of the machine. The men trusted the design, and the design failed them not because it broke, but because it didn't understand the chaos of reality. The titanium Icarus did not fall because it was weak. It fell because it was too specialized. It was optimized for a specific type of war that never happened, and utterly unprepared for the accident that actually occurred. It serves as a reminder that in engineering, as in life, graceful failure is just as important as high performance. A system that works perfectly right up until the moment it kills everyone is a failed system. As we look back at the Cold War, it is easy to focus on the politics and the missiles. But the Komsomolets reminds us that the conflict was fought by men who lived on the razor's edge of technology, in environments that were hostile to human life. They were explorers as much as they were warriors. And like all explorers who pushed too far, some of them did not come back. If this deep dive into the hidden history of the Soviet Navy and the cost of extreme engineering meant something to you, we'd be honored to have you with us again. Until next time, stay curious and take good care.